Hi all, in the previous lectures we had discussed about quantization process and quantization noise. Today we will start our discussion with a very interesting topic which is pulse code modulation or PCM. Okay, so pulse code modulation is a digital modulation technique where we we actually convert an analog signal or a continuous signal into a digital bit stream or encoded digital signal. Okay, as you can see, the block diagram of transmitter, transmission path and receiver is depicted in this slide. Here the different processes which we are going to carry out so as to convert an continuous time message signal into a digital bit stream is explained. So the first block what you can see is source of continuous time message signal. It might be an audio signal or it might be an video signal or it might be any computer data which is analog form. Okay, now it is first passed through a low pass filter which is actually an anti-aliasing filter that you have understood in the sampling theorem. Then the low pass signal is now passed through a sampler which samples the signal more than Nyquist rate, that is using the sampling frequency more than the Nyquist rate. Then the signal is quantized. After that it will be passed through encoder which represents each of the voltage levels with certain number of bits. Okay, so that is the general explanation. After that signal is uh, put onto the channel where channel carries the digital encoded signal. Now as the signal goes through the channel, it is get attenuated or it is affected by the environment of the channel or the surrounding environment of the channel, and it degrades in its strength so as to get back its strength or so as to reshape the signal which has been distorted. We use regenerative repeater regenerative repeaters at particular distances, and they will regenerate the signal or they restore the shape of the bit stream. Now the regenerated signal will be received at the receiver circuitry or the receiver end, and final regeneration before the signal is decoded will be done. Once the shape of the signal is restored by the regeneration circuit at the receiver end, the signal is applied to a decoder which will decode the digital bit stream and gives us what? The voltage levels. Now these voltage levels, if passed through a reconstruction filter having the same bandwidth as that of the message signal bandwidth, then we will get a smooth message signal which we had transmitted, and then it can be applied to a particular destination device. It might be loudspeaker or it might be a display screen or any other output device. Okay, in that way our pulse code modulation works. So this is the example of pulse code modulation with illustrative waveforms. Here you can clearly observe that the message signal m of t from the source whatever we are getting, it is having some kind of high frequency noise. When it is passed through a low pass filter or anti-aliasing filter, we get the signal with desired bandwidth only. Now this signal which is low pass filtered, now this signal which is low pass filtered is applied to a sampler which is an electronic switch, you can say, where the signal is sampled at the rate greater than the Nyquist rate, and the output you get is signals at discrete time levels, but amplitude is not discrete, which is required in most of the cases. So amplitude might be 1.21, 2.13, 2.8345, like that, different voltage levels which might be continuous because the signal is continuous when it was sampled. That's why we apply the signal to a quantizer so as to get the discrete voltage levels, so that we can encode the voltage levels in the next stage. The signal is applied to quantizer in the next stage, where we have chosen level 4 quantizer, where 4 voltage levels we have designed such that any voltage between 0 to 1.5 we will quantize it to 1 volt or rounded off it to 1 volt. Any voltage between 1.5 and lesser than 2.5 we can round it off to 2 volt, and then voltage between greater than 2.5 and lesser than 3.5 as 3 volt. Similarly, voltage greater than 3.5, greater than or equal to 3.5, and lesser than or equal to less than 4.5 as 4 volt. So we have got discrete voltage levels as well as discrete time interval. Now each of these voltage levels we can encode using an encoder. Since we have only 4 voltage levels, so using 2 bits we can encode 1 voltage level. That's why we have chosen R, or sometimes it is called as small n, is equal to 2. So 1 volt will represent by 2 bits such as 0, 0. 2 volt we can represent by 0, 1. 3 volt we can represent by 1, 0. And 4 volt, this voltage level 4 volt we can represent by 1, 1. So this discrete signal or the quantized signal is now represented as 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0. So this is our pulse code modulated signal. Now this signal is transmitted through the channel. You can see this channel, right? So as it travels through the channel, its voltage levels are degraded by because of number of reasons, and we need to restore these voltage levels. For that purpose we have regenerative repeater. When it is passed through regenerative repeater, it works in such a way that the voltage levels are restored again. So here these are the voltage levels restored, and these regenerative repeaters needs to be kept at certain distances where we can easily recover back our signal. And at the receiver end, again the signal will once pass through the last regenerative repeater. Here you can see that, and then the signal is applied to the decoder, and decoder converts the digital bit stream into the corresponding voltage levels. And here this signal is now we are going to apply to a low pass filter which smoothens the signal, and this will be an approximation of our message signal which we had transmitted. So in this way pulse code modulation works. Okay, I hope you have understood this concept. The same has been explained in these points. You can go through it. So coming to the next concept, which is regenerative repeater. Here we are going to understand about the regenerative repeater in detail. So this we'll see in the next session.